Okay, thanks a lot. Yeah, I'm going to talk about divergences. And this is joint work with Marco, who's also here. And see how I should. So this is basically, I don't know, the fourth or fifth information theory session. So I guess I don't really need to convince people that divergences are like important quantity in our field in like very diverse forms. And I maybe short warning at the beginning, this is not really any like application talk or something. I'm not even gonna have like information theoretic protocols or anything. We are really focusing on these quantities and their properties and how to define them. Okay, so I hope that's interesting to you. And where do I point this? Where do I need to put this one, right? Okay, thank you. Okay, so let's talk about these divergences. I start with like an example that I guess most of you have seen. This is just the definition of the relative entropy. And this is a classical definition on like two probability distributions. And now we want to, of course, look at quantum generalizations of these quantities. And in fact, we have like a very simple, I don't know, like methodology, how we can go from a classical to a quantum quantity. And that is basically we just replace the sum by a trace and all p's by rhos, the q's by sigmas. And now we have a quantum quantity, right? And now for most of the time, you just take this as the right quantity somehow. But in fact, it's not that obvious that this is the right definition of this quantity and that you shouldn't be doing something else. Now it turns out for the relative entropy, there's a lot of work on this quantity or using this quantity. It has a lot of operational interpretations. So we have kind of agreed that this is the, in some way, correct definition of a relative entropy in the quantum setting. Of course, there are other ways to define them, but this one is like the one we deem most relevant. Then there are lots of other different divergences, and often these are families of divergences. So in particular, they're the Renyi divergences. In the classical case, they're just defined like this, so based on a parameter alpha. And now here I can give, or I can kind of use the same recipe to get a quantum version of this quantity, but I can also somehow write this in different ways and get kind of different quantum versions of this quantity, okay? I kind of use the same recipe, but I write it just slightly differently. Turns out these are different quantities. And what kind of is different compared to the relative entropy is that now I have these two different quantities and they're both operationally useful, even through their different and both like natural generalizations of the classical quantity. And just for completeness, the title of the talk was also about f-divergences. So this is a different definition of a divergence. Now, instead of a parameter alpha, we have like a class of functions f that define this classical divergence. And again, there are different ways how to translate this to the quantum setting. And it's not so clear which of these definitions is like the correct one in some way, or like the one that we should use. And the first one I wrote down is kind of just because it's the one that kind of most naturally follows like this recipe I described. But the second one, the Petz F divergence, is actually the one that's most commonly used in the literature. And yeah, so now we have this whole zoo of quantities basically, and we want to kind of narrow down which are the ones that are useful. We do this with operational interpretations, and especially in the Renyi divergences, like both of the generalizations I've written down have these operational interpretations. So maybe we look at properties. Yeah, which of those have like nice properties for like different parameters of alpha. And the most fundamental property of any divergence is data processing. That means if I apply a channel to both arguments of the divergence, value of the divergence can only go down, okay? And if I look at data processing for these Renyi divergences, turns out the classical quantity has this for all alpha. So we look only at positive alpha, but for all of them, it obeys data processing. However, the quantum generalizations do not have this property in general. So there are very specific ranges of alpha for which this property holds, this data processing. And this kind of motivates the question if there's maybe a nicer generalization of these quantities to the quantum setting that has like the nice properties of the classical divergences in at least the same range of parameters and the same generality as in the classical case, but hopefully also like similar operational interpretations. And kind of what do we do if we are like kind of explored all of the quantities that we have sufficiently to kind of have all the properties, but we don't have, like we are not fully satisfied yet with what we got. So we kind of go and we get a new quantity, okay? We want to define something new that hopefully behaves better than what we had before. And now there's a lot of different ways of defining new quantities, right? If you remember these alpha Renyi divergences, you could shuffle around these states like a lot more and get like different definitions, but we actually kind of already explored them and we know that they're not more useful than the ones that we already found. So what we are doing in this talk is basically we take a step back, we go to the classical setting, and we find a completely different way of writing these divergences. And for that, we go to work that was actually fairly recently published by Sarsen and Verdu, and they gave an integral representation for these f-divergences. So we later see how the Renyi divergences relate to these f-divergences, but for now the f-divergences are kind of the most general case that we can look at. Okay, and they showed that any of these f-divergences for like a class of functions f, that's fairly general, so we will look at convex functions f with some normalization, can be written as this integral that as in the argument basically only has the function f, or here the second derivative particularly of the function f, and yet another divergence. And this divergence is called the hockey stick divergence. For the classical case, you have the definition in the upper right corner. And okay, the common question at this point is like, why is this quantity called hockey stick divergence? Just because it looks like that when you plot it. And the nice thing is that this quantity actually also came up in a couple of different contexts recently in the quantum information literature. So we do actually have a quantum generalization of this quantity, okay? And we kind of do the naive thing. We take this classical hockey stick divergence and we replace it by its quantum version somewhat, okay? So exactly the same thing. Now we have a quantum divergence. And this might seem fairly naive, but now we kind of need to start doing work and to show that this is actually a good divergence and that it has nice and interesting properties. Okay, so the first thing, we check like the basic properties. Yeah, is this quantity any of the known quantities and is it useful? And first we check, okay, it has like data processing, it has like convexity, it has like, it reduces to the right quantity for classical states. And in fact, none of this is actually surprising because we get all of this more or less for free from the properties of this hockey stick divergence, because that's a nice generalization of the classical version and it obeys data processing, convexity, and so on. We kind of get like all these desirable quantities for f-divergences for free. So the next thing we kind of want to check is that what we're doing here just reproducing stuff that we already know? Is this like sorry, this is like a quantity that we have been already working with. And the first thing we check is, does this correspond for the right function f to the relative entropy? And in fact, most of the work here was actually already done by Peter Frenkel in a very recent paper from 2022. And he gave an integral representation for the quantum relative entropy. Okay, the formula, I just put it here, but it's not too important, but the main point is if you do some additional work, and I'm also pointing here to a paper by Anna Yankova, who already did some work in this direction, you can actually get an expression of this integral representation that corresponds exactly to that which I presented on the last slide for a specific function. So if I choose this function to be x log x, then I just recover the relative entropy, okay? And this is actually a very technical result and not trivial at all. So we are kind of lucky that there was already this very good work out recently before ours. And that's a great start because the relative entropy, as I argued on the first slide, is really the relative entropy is really the most important divergence in some way that we most commonly use. So it's somewhat nice that we recover this quantity. But of course, it's not so interesting if we just in general recover, like, I don't know, all the pets quantities or something. So the next step, we go to Renyi divergences. And those are, so Renyi divergences are not directly f-divergences. But if we choose this very particular function up here, so the main thing is kind of this x to the power alpha, which you probably recognize from the Renyi divergences, then we get a related divergence, which is called the Hellinger divergence. And these ones are by this formula directly related to the Renyi divergences. Okay. So first we can kind of check the properties if this is a good Renyi divergence. And in fact, just from the properties of our integral representation, this must obey data processing for all alpha. Okay, and that already tells us that this is none of the quantities that I showed you on the first slide, because simply none of them, like none of these quantum generalizations actually obey data processing in this whole range. Okay, so that's kind of nice, but the question is what can we kind of do with this now and what can we say about this quantity? And the first thing, very naively, what we do is we plot this quantity, okay? And indeed, we compare it to some other definitions and we see, okay, it's not the same, that's nice. But we also notice something maybe peculiar, which is that this quantity is for alpha larger than 1 is smaller than the sandwich Renyi divergence. And now I haven't discussed this before, but the sandwich Renyi divergence is particular in the sense that it is the smallest quantum Renyi divergence that obeys data processing and is additive. Okay. Now ours obeys data processing, but is even smaller, hence it cannot be additive. Okay, and generally additivity is something that we look for in these properties because it's a very useful property. But in this case, it gives us a natural idea, which is we can just look at a regularized version of this quantity. Okay. So in this case, I look at n copies of the states, and I just kind of normalize by this 1 over n, and I get the limit of n to infinity. So this kind of, in the hope that this will make use of this non-additivity, and maybe it will, generally this will recover the additivity. And now we kind of come to the first main result, because we can actually say something interesting about this regularized quantity, which is depending on the range of alpha, we exactly recover those known Renyi divergences that are presented on the first slide, so the pets and the sandwich Renyi divergence. And what is, I think, most remarkable about this is that we recover them in very particular ranges of this parameter alpha, which is exactly those parameters of alpha in which these quantities are generally useful. So if you look at, for example, hypothesis testing applications, these two quantities will appear there, and they will appear exactly for these parameter ranges. So in some way, our divergence provides some kind of like parent quantity for these commonly used Renyi divergences, and gives like somewhat like a common explanation why exactly these two quantities might show up in these applications. In fact, it was in some literature, some parts of the literature was proposed that this like pieced together definition of the Renyi divergence might actually be the most useful or the correct quantum generalization of the classical Renyi divergence. Okay, so before I move on to some properties, I want to kind of introduce one more divergence, and that's the so-called chi-square divergence. And actually, there was a nice talk on, I think, on Monday that talked a lot about this chi-square divergence in the context of algorithms on the algorithm session. And they choose a very particular chi-square divergence as like a measure of distance for like, or some quality measure for the algorithm. And how do we generally define these? So these are usually defined as a very particular second derivative of f-divergences. Thanks. Yeah, and what is kind of interesting here is that the second derivative for our function is not dependent on the function f. And this is actually not true for any other of the known f-divergences, which usually makes working with this chi-squared quantities a bit complicated and also a bit random because you don't know which of these you should actually pick. But if we use our f-divergence, we get a very particular particular definition for this chi-square divergence, which actually coincides with the Hellinger divergence of parameter alpha equals 2. Okay, and okay, just as a remark, what I already said. So if you look at the pets, for example, which is most commonly used, you get a whole family of these divergences, not one particular quantity. And I'm going to refer to this paper for more details. And what is also nice, the second derivative, we can actually calculate it. So, or it's actually known how to calculate it because we know the second derivative of the relative entropy. So this actually gives us expressions for the chi-square and, for example, the Renyi divergence of order 2 for our quantity. So maybe also hint where to go with these quantities to get like a non-integral representation expression for our divergences. Okay, so now I want to briefly talk about some applications in like the last, okay, I see only like 3 minutes. Like I said, the most important application, or the most important property of divergences is data processing. But in many cases, we actually want something stronger. We don't just want to know data processing, we want to also know how much kind of does this reduce? Like, is there a constant we can put there that's smaller than 1? Yeah, that kind of makes this a stronger inequality. And for this, we define these contraction coefficients. And for like the most, or lots of interesting known work about these for the PETS definition of these divergences, I refer to this paper here by Hyai and Ruskai. And okay, there's an important special case is that we can define this for all f divergences, but also for the trace distance, basically. This is like a very commonly used example of these contraction coefficients. And now, using our divergence, we can actually say a lot about these contraction coefficients that was not known or probably doesn't hold for the generally used f divergences. And a remarkable result that's actually very simple to prove with our divergence is that this contraction coefficient for the trace distance is always an upper bound on that for almost any f divergence. Okay, and this includes, of course, the relative entropy, for example. And even in that case, it's a new result. So this somewhat often easier to handle contraction coefficient. If I have contraction for the trace distance, it also tells me automatically a certain amount of contractions for, let's say, the relative entropy or the chi-square divergence. Other results are that, for example, the contraction coefficient for the chi-square divergence is actually a lower bound for most f divergences. And we can say something even stronger, which is if the function f is operator convex, then all these contraction coefficients are actually the same, which was like, this is actually a very heavily exploited result in the classical setting, but it was completely open in the quantum setting. And I think most people working it assume that for the PETS definition of the f divergence probably does not hold. Okay, and again, this operator convex function f, this includes, for example, the relative entropy as an important example. Very good. So just some other consequences of the definition of our f divergence is that we can actually use properties of the hockey stick divergence to prove also bounds on, or like properties of our f divergence. So in particular, we can give upper bounds on the hockey stick divergence. It's obviously always, so for 1, this is just the trace distance actually. But we can give tighter bounds, and using these bounds, we can give, for example, types of like reverse Pinsker inequalities. So we can bound the relative entropy, for example, by the trace distance with like some coefficients that mostly depend on like the max relative entropy. Okay, and okay, some plots. Don't look at these too closely, but the main point here is that these bounds outperform basically, at least in some ranges of states, all the previously known bounds. In particular, the famous ordinate Isard bound, which is one of these. And one maybe interesting observation is, which one can see in the left slide, on the left side, if we take, for example, qubit states that commute, then this first inequality here is actually an equality. So this is a very tight bound in general. Yeah, so for some ranges, this will commute, will be optimal. Okay, and just some other examples. We can, for example, get strengthened Fuchs-van der Graaf inequalities, so relating, for example, the fidelity and the trace distance. We can get kind of like continuity bounds. I'm now just giving you an overview. If you want to see like details, please hit me up later or have a look at the paper. But just kind of to tell you what all kinds of things we can do with this quantity. And of course, also, I put them for simplicity, I put them for the relative entropy or fidelity, but in principle, we can get bounds like this for any of these f-divergences. And there's a connection to also differential privacy, which I kind of give like an example here. We can find results like a quantum Stein's lemma under differential privacy. And this comes back to this very natural definition or very natural connection between differential privacy and the hockey stick divergence. So basically, knowing a lot about the hockey stick divergence allows us to prove all kinds of things. And I think that's basically it. I put some challenges here, but I think I'm like a minute over time, so I just put them here. And maybe for those very familiar, those are like my favorite open problems that would be nice if anyone can give some insights on those. But yeah, thanks for your attention.
Now, if we have any questions. I'll take advantage of this opportunity. How should we interpret this non-additivity of your divergence and the need for regularization? Is it possible that we sort of should think of, well, end of question.
I think one way kind of to think about this is that this hockey stick divergence shows up very naturally in the context of hypothesis testing. Like you can express, for example, like the basic problem of like symmetric hypothesis testing as the hockey stick divergence, or as like a function of the hockey stick divergence. And there you have the same non-additivity property, right? The Chernoff, like this thing, when you want to prove like a Chernoff bound asymptotic static or something, you also need to somehow overcome this non-additivity property. And that, I would say that's basically where it comes from. Also the proofs showing the asymptotic behavior, the proofs are basically based on hypothesis testing techniques in the end. Yeah.
Oh, here we go.
Thank you. That was a very interesting talk. So I guess one question I have is, do you have any intuition for this integral representation over the hockey stick divergence? Like, you know, if you have a Fourier representation, you can kind of interpret the coefficients one way. Do you have some sort of intuition here?
Not really, actually. It's a very good question, but like why exactly the function appears in that way is not that clear. Like you can look at the classical proof and see why the functions show up exactly in this way, but like I don't have an operational interpretation why they have to be exactly this way. In fact, one of the open problems is actually, it seems like this is very closely related to like these hypothesis testing problems and all, but it would be nice to actually prove that there is like an operational meaningful interpretation for like our quantity directly instead of the asymptotic limit. But that would require to understand where exactly in the proof you need to put this integral into your work. So it's kind of, yeah, it's a bit complicated here.
Yeah, thanks. That's very interesting.
Yeah, so you have the contraction coefficient of trace distance upper bounds, your f-divergence contraction coefficient. I think you also have the other way, right? You can also upper bound the contraction coefficient of say relative entropy by that.
Sorry. So upper bound for the relative entropy by...
Can you upper bound contraction coefficient of trace distance by relative entropy or any of your divergence?
Oh. Yeah, I guess you can. I guess you can, but there will be some additional factors like some smallest eigenvalue things.
Okay.
In fact, you can, this lower bound that we have in terms of the chi-square divergence,
Yes.
you can also get an upper bound in terms of the chi-square divergence,
Yeah.
but that will require like a 1 over some possibly diverging parameter or something. So it's not as nice, but you can get an upper bound. And then from there, you can bound it again by any of the other divergences.
I see.
But
Okay. Thank you.
Thank you very much. Let's thank Christoph again.